Hello everybody. In this video I'm going to be solving a problem from the AIME in 2013, problem 13, and I'm going to be using barycentric coordinates. So we're given an isosceles triangle ABC, and we define two special points here. So D is on side BC, so that the length CD is 3 times the length of BD, and then E is the midpoint of AD. Now, we're given the lengths of CE and BE, and we want to determine the area of ABC. So, what we can start with is finding the barycentric expressions for all 5 of these points. So, we know by definition the coordinates of our vertices A, B, and C are fairly simple. A is 1, 0, 0, B is 0, 1, 0, and C is just 0, 0, 1. So let me write that in. D splits BC in between, or sort of into a 1 to 3 ratio, right? So this is a 1, this is a 3. Well, ratio-wise, it's not necessarily 1 and 3, which means that D, we know that any point on the line BC must have an x value of 0, and since it's 3 times as much to, or it's like 3 times closer to BC, sorry, 3 times closer to B, then it should be 3 times the y value and 1 times the z value. And remember that all normalized points in barycentric coordinates add up to 1, so we can divide by the sum of the coordinates, which is 4, and we get 0, 3/4, and 1/4. And this is a D, not a P. It kind of looks bad. Okay. Now E is the midpoint of AD. And midpoints, just like in normal coordinate systems, you could just average the coordinates. So if I add up A and D and then take 1/2 of each coordinate, I get 1/2, 3/8, and 1/4. So now we have the coordinates of all the 5 points. Now we just have to use the information given to us. We know that BE is a length of 3 and CE is a length of 7. So we can use the distance formula and find expressions for these lengths. So what we want to set up are displacement vectors BE and CE, and a displacement vector is just like in normal vector systems. You basically take the coordinates of your ending point and subtract the coordinates of your initial point. So this would be the same as, say, E minus B, right? So E minus B, vector-wise, right? So we're just subtracting the coordinates. So 1/2 minus 0 would be 1/2 here. 3/8 minus 1 would be -5/8. And 1/4 minus 0 is just 1/4. And then we can something to that should be right. Anyway, then CE is defined similarly, where we take the coordinates of E and we subtract the coordinates of C. So we get 1/2, 3/8, 1/4, but we're subtracting 1. We're only subtracting 1 from the last one, so it's 1/2. Oh, I know my problem. Sorry. This here, this should be an 8 because I divided by 2 here. I was checking in my mind; it wasn't coming out right. This is 3/8, and then 1/8 minus 1 is -7/8. So we get that for CE. And now we can use the distance formula, which says that the distance, or the length of a displacement vector is equal to the cyclic sum of -a squared yz. And by cyclic, we just mean a goes to b, b goes to c, and c goes to a, x goes to y, y goes to z, and z goes to x. So we get 3 terms in this sum because we're cycling a, like a goes to b while y goes to z, and so on. So if we use this formula, we notice that we have a, b, and c, right? Those are the lengths, basically the length of the side across from the corresponding letter of the vertex. It's like A, capital A corresponds to, is across from the length of A. Well, A is equal to B. So for each distance, we're going to get 2 expressions, 2 equations really, that involve A squared and C squared, because our B squared term is just an A squared. So we're going to get 2 equations for the distance squared. So CE squared, right, is going to be 7, and BE squared is going to be 9. So we get 9 equals the cyclic sum of -a squared yz, where x, y, and z are these values. This is x, this is y, this is z. And 7 is equal to the cyclic sum of -a squared yz, where these values are x, y, and z. We're pulling from CE. And I'm going to spare you the algebra, but obviously we're going to have 2 equations that are linear with respect to a squared and c squared, right? It doesn't matter that they're squared. What matters is that they're both squared. Really, they're just 2 variables. And what's nice is that this is an isosceles triangle, right? So when we drop this, right? So imagine this is c halves, so I'm cutting it off here. This is c halves, and this is a. Well, the area, right, is just c halves times this length, which we can get from the Pythagorean theorem because this is a right triangle, if we know a squared and c over 2 squared. So one thing that makes solving this equation nice is that if you substitute, let's just say b, I know it's bad to use the same, a variable here, but if you say b is equal to c over 2, you can solve for c over 2 squared directly, and then it makes, doing the Pythagorean theorem thing a whole lot easier. And I'm going to spare all the algebra, but what you'll get is that a is equal to 4, and b is equal to the square root of 7. And in other words, this length, the height of the isosceles triangle will be 3, and so the area of the triangle will be 3 times the square root of 7. And another cool thing to notice is that since BC, which is A, is equal to 4, you notice in this picture, right, this BEC actually kind of looks like a right angle, and it is, in fact, a right angle, because 3 squared plus square root of 7 squared is 4 squared. But anyway, that's just an interesting thing. I don't know if there's a way to prove that this is 90 degrees and then get your answer. But anyway, thank you for watching, and I'll see you in my other videos.